This is the arguably the simplest measure of complexity of a function. You will realize that when we talk about computing a function, we will discard most of the things and we will take the simplest measure of complexity that will be called deterministic pre-complexity. And when I say simplest, I mean in the computation. The problem in the computational world would be that you are given a function. You can say 0, 1 to the n to 0, 1 or -1, 1. The things remain the same. I will switch between the two. Should not get confused with that. Let's keep 0, 1 for today. Okay. You are given a function like that, and when we say that you want to compute this function, what does it mean? This would mean that as an input, you will be given some x, which is the element of the Boolean hypercube, and you need to devise an algorithm which works on any input, correct? So devise an algorithm on your favorite computing machine such that your output is f of x. I have written things in the wrong order. I should say that your algorithm should be designed without the knowledge of x. In that sense, the algorithm should be independent of the description of the algorithm should be independent of that. And actually, if you think about it, most our algorithms are independent of n also. Right? When I say independent, again, it is very intuitive sense. I'm not trying to formalize it, but you would see that it is if I give you the algorithm for 2, 3, 4, 5 up to 10, generally my algorithm is extendable to any n. The algorithm for input length 10 and the algorithm for input length 15 is not very different. As human beings, once we see the algorithm for n equal to 10, it is very clear to us that how we will define an input. We will define an algorithm for input n is equal to 50, correct? And this thing is called what in computation?
Induction.
No. Induction is a mathematical concept. I'm looking for a computational phenomena when your algorithms are similar across.
Uniformity.
Very nice. Yes. This is called uniformity. And that is why generally when an algorithm is given to you, you can talk about the asymptotic complexity of a function. Correct? So, or asymptotic complexity of an algorithm. You can say that, okay, when I run that algorithm on an input of size n, how much time it will take as n increases. And we are going to ignore constants. Anything which is like square root of n, 2 times square root of n is same as 3 square root n. You guys have a lot of experience with that, right? And this we will remember now in the sense that we will be interested in the asymptotic complexity. Most of the time, when we say complexity of the function, we are going to be talking about asymptotic complexity of functions. The kind of functions we talk about, or and majority, it is quite clear how to keep its definition uniform across all the inputs. This is just repeating what we have seen before, nothing new, but just wanted to emphasize since we are going to explicitly see a complexity measure. Let us start. I know Udit is familiar with decision tree complexity. Is there anyone else who knows what decision tree complexity is?
So Udit was once giving a talk on this, so I just remember a bit from it.
Okay, okay. Don't worry. The concept is very, very simple. In some sense, we are going to discard all the difficulties in making an algorithm. How are we going to do that? Remember, what is our objective? The objective is to compute the value of the function given a certain input. And since we are talking about Boolean functions, we will remember that our f is a Boolean function. This implies that our input is going to be in string of length f, some element of 0, 1 to the power. Any algorithm of that kind will access the input, correct? Without knowing the input. If your function is non-trivial, it is not a constant function, you have to query your input. This is so obvious that this might confuse you. Now, why am I saying this? But it is dead obvious, right? If the function has to compute the value f of x, then it should query x. It should find out what is the value of x1, what is the value of x2, right? I can think of my input as n variables, x1, x2, xn, where xi is the ith bit of x. Any algorithm, what form of will be of the algorithm? It will ask, what is x2? What is x3? Then do some computation. Then what is x5? Do some computation. What is x6? Do some computation. Then finally say, oh, I think the function value is 0 or less. And this model we are going to formalize. To formalize this, one of the important concepts is of a black box or an oracle. Think of the input as being hidden by a black box. Unfortunately, it's a red box in my diagram, but black box means you don't care how it works. You only worry about the functionality. And what is the functionality? If you give it index I, it will churn out value x. And in this complexity model, you want to compute f of x, but minimize the number of queries to this black box. What are the general measures of complexity in computation? Do you always only worry about the queries?
Time complexity, space complexity.
Right. Generally, we worry about time complexity, space complexity, but we want a simpler model. And in that model, we are only going to count the number of queries. Again, what will be the algorithm? It will, again, the input is hidden. It just can't see all the input. It will say, oh, tell me x2, tell me x3, tell me x5, do some computation, then realizes, oh, I probably need x6 or x10, ask x10 to the oracle. And then finally it will output the answer. The task of the algorithm, the complexity of the algorithm is the number of times it queries this black box. This is the most important part. Probably it is going to take exponential of xi. Probably it is going to do a very, very complicated operation between x1 and x2. We don't do. Probably it is going to take a very, very complicated operation between x1, x2, x3 up to xk. That might take a lot of time, but in this simple model, we are not going to do. The only thing we are going to take about is number of queries to the black box or and I think if you are a fan of matrix, I don't have to tell you why I'm calling it an oracle. right? And this is called the decision tree complexity of the algorithm. I will come to the decision tree complexity of the function, but let's talk about the decision tree complexity of an algorithm, or what is a decision tree algorithm. And it is called a decision tree because the algorithm can be viewed as a tree. Let's see how to view this decision tree, this algorithm as a tree. You start by asking some input variable x1, then you do some processing, but there is only two ways in which Oracle can answer x1. It can answer 0 or 1. Looking at 0, this edge represents some kind of computation which I don't care about, but then it goes to some bit x5. If x1 was 1, it could be something like x10. And then again 0, 1, again some inputs, and after some time, once I have queried some of the variables, I'm sure that if I've queried these variables, then my value is 1. And similarly, there might be a path where I query, let's say, x98, and I say that the value is 0. This represents an algorithm. Other way to say it is an algorithm on a particular input queries some bits xi1, xi2, xik, where xij can actually depend on the value of xi1, xi2 up to xij. This is saying that my queries are adaptive. I am just trying to describe the algorithm in multiple ways so that you are clear. When I say that this is a decision tree algorithm for a function, you should be clear what it is. If you are clear about it, then we can go to the complexity measure. So before that, does this seem okay? Questions about this?
So exactly one tree is going to correspond to exactly one algorithm.
Sorry, one tree is going to correspond to one algorithm. That is correct. Yes.
Okay.
A tree contains the label of the nodes also, right? So what you are writing on the top of a node is also important.
So basically, if we are querying these bits, these particular bits, xi1, xi2, xik. So just basically, if we want to compute f, a Boolean function f, so the function, if it is, we are saying that it is dependent only on these inputs.
See, the point is that these are adaptive queries, right?
Okay.
If those were non-adaptive queries, then you can say that the function depends only on those particular bits, right?
Okay.
But in this case, depending on the input, you can go to a different path, and you will be doing different queries. So there is no single set of queries which you will be doing, right?
Okay.
So you can't say that in this case, x1, x10, let's say, there are only certain inputs for which I will be following this path. For those inputs, you are correct that the function only depends on x1, x10, whatever is written here, x98 or something. But for all the other inputs, that is not true. For the other inputs, they might depend on x1, x5, and so on.
Okay. So even that can be, that complete picture, whether it will be dependent on this, the adaptive nature, can it be captured via a Boolean function?
Oh, you are saying that no, these are in some sense certificates, right? These are partitions,
Okay.
partitions of your input space, where each partition has the same function value, correct? So we will do different attempts to kind of capture the same thing which you are saying, right? But those will not be, I don't think those can be as simple as a circle.
Okay.
Sorry, I mean as simple as a Boolean function.
Okay. Sir.
It will be a bunch of Boolean functions, right? But we will see that. This is a good point you have made, that yes, there are certain set of inputs for which the function only is dependent upon just a few variables, but that how to capture that is not an easy task. That we will spend significant time worrying about. Okay. Yeah. Yes. Okay. Now, first question is, what is the complexity of this tree, or what is the, I should say, in quotes, running time, because there is no time concept here. It's only the number of queries. So if I ask, what is the complexity of this, or what is the, how expensive is this algorithm for me? What will be your guess? Given such a tree, what is the complexity of the tree?
Depth of the tree.
Very good. This was pretty obvious, right? The depth of the tree is the complexity of this algorithm. And then what should be the complexity of a function, or I actually denote it by T of f. This is called the deterministic pre-complexity. What should be the deterministic pre-complexity of f? Remember, there is no single algorithm to compute f, right? For example, sorting has many ways to solve it, right? But if someone says define the complexity of sorting, what will be that? If there are several algorithms to solve a problem, which one would you like to pick?
One with the lowest running time.
Exactly. The deterministic pre-complexity is minimum over all trees which compute f. This you will easily be able to see that there are multiple decision trees which can compute a single function f. This is not hard, and you will see it. But that if you take all the trees which compute f, that means they give the correct answer for f. You take the minimum complexity of those. You consider all trees which compute f, take the minimum complexity of out of all those. That will be called the deterministic decision tree complexity of f. This word deterministic might be confusing to you at this point, but don't worry, we will extend this model and you will be pretty clear that why we are calling it a deterministic. One simple way to think about it is that in this case, our definition that trees compute f is very strict. We should compute f correctly at every instance of the algorithm. Every input, every instance of the algorithm, whenever we run it, we want the tree to compute f correct. But let's go into this later. If you have heard of randomized algorithms, then this deterministic should be clear. If you have not, we will talk about it in the next class. Let's call it decision tree complexity for this lecture. So the definition of decision tree complexity of f is clear. You define all possible decision trees which compute f, pick the one which is the best. What is the best which has the minimum complexity? The depth. Remember, the complexity of the tree was the depth. This is too many definitions, and I think the best thing would be to take an example. Let's take the favorite function OR and talk about what is the decision tree complexity of OR. What do you think? Can you come up with a decision tree for OR? Let's just try to give at least one decision tree for OR.
Sir, should it be n?
Okay, yes, it is going to come out to n, and the easier part is to show that there is a tree of size n which computes n OR. And what is that decision tree?
Basically, I mean, it will be kind of a binary tree of, should I say, a complete binary tree? Because
Is it going to be a complete binary tree? Okay,
no,
let's
no,
think.
no. As soon as you get a 1, you will automatically say that the output is.
Correct. Let's start with x1. There are two possibilities, 0 or 1. I'm starting with x1 because OR is a symmetric function. It doesn't matter which one I start with. Right? If x1 was 1, then what do we know? That the function value is already 1. I am done. And this branch will never proceed. But if it is 0, then what?
We query x2.
Yeah, you can query x2, x3, whatever you want. Again, 0. So this is actually something completely opposite of a complete binary tree, right? It is a very, very lopsided binary tree. But unfortunately, the depth of this tree is
n,
right? And if you think about it a bit, it seems hard that you can prove that the decision tree complexity is equal to n, but it seems like it should be n. There doesn't seem like a better way to do it. All of you are familiar with complexity. Whenever we talk about algorithms, most of the time, giving an upper bound is easy. In this case, we said d of OR is less than equal to n just by building this tree, and it was easy. But then any reasonable complexity theoretic person would ask the next question, is this tight? Can we show that d of OR is actually greater than equal to n? This is lower bound, which is obviously more, or not obviously, but most of the time, this is the difficult part. We want to show that no matter how you construct a decision tree, right? Let me just write it. What do you want to show? You want to show no matter what decision tree you pick, if it computes OR, if it gives the correct answer on OR, then what do I want to show? Sorry, I didn't hear. Then the depth is, by the way, does it make sense to have a decision tree with complexity more than n? Obviously no, right? The total number of variables are n, so there is no point taking more than querying a variable again. Once we have the variable, we can just remember its value. There is no point querying it again. The maximum depth could be n, or that maximum decision tree complexity of a function could be n. You want to show that for OR it is the highest. How will you show it? What will be your answer?
I mean, basically, or can become one if even one of the inputs is one, right?
Correct.
So the worst case will be when you go into a path of 0, 0, 0.
Right. Right. Very good. This is the central idea, and I think most of us are convinced. But how will you formally show? Slightly, can we make it slightly more formal?
So let's say there is a tree of depth n-1, then
Okay, very good.
yeah, then all those queries will be 0 and the remaining bit will be 1. So for that input, it will not compute, the function will not compute a correct output. The tree will
Very,
not compute a correct output.
very nice. The kind of argument you are making is called adversary argument. This is going to be very simple argument in this case, but this is very, very powerful. You will see that in many, many occasions, in many different models of complexity. Decision tree is the first one. We are going to know randomized query complexity, quantum query complexity. We will study many of these. And this adversary argument is very, very strong. That's why let's pay attention to the simplest case of this adversary argument. Who is the adversary? The adversary is the person who is trying to prove that the function is typical. Or in this case, the adversary is the person who is trying to show that you will need at least n queries to find out. Now, given an algorithm, what does the adversary do? Adversary says, let's pick the first value, first index. You must have asked some index here. Whatever you have asked, I will give you. Then depending on my answer, you will again ask something else. Let's say xi2. I will again answer. Since you have claimed that you are computing on an n-1 queries, after querying, let's say, the n-1th bit, you will say that you know the value of the function. But can you? You can't. Because by setting xin, the remaining bit, to 0 or 1, my function value can change. I am able to construct an input, a partial input, such that after you have queried everything, there are two possibilities. The function could be 0 or 1. But your algorithm should have decided whether it was 0 or 1 because the depth of the tree was n. Hence, this tree cannot compute the function of. Okay. Does this make sense?
Yes, sir.
Are you convinced that the d of OR is greater than equal to n, which implies actually that d of R is exactly. We saw that it was less than equal to n. Now we showed that it is greater than equal to n. That's why we figure out that this is equal.
Just a small thing. Instead of n-1, we should say it for some k less than n, right?
But the same argument will work.
Yeah, the same argument applies.
Right.
So a decision tree should compute f for any input.
That is
It
correct.
should
Yes.
the same
Uh,
decision tree.
The same decision. Yes. This is going to be actually a point which you have to remember even when we change our model of randomized decision tree, quantum decision tree, in all of those, our decision tree should work for all inputs. We might have some other coin tosses, and depending on the coin tosses, sometimes we get the value, sometimes we don't. That is allowed. But we should always answer correctly on every input. We will never say that, oh, some inputs are fine. On some inputs, I don't care what you ask. Okay, so whatever is the domain of the function, on that domain, my function should, my algorithm should answer correctly. Sometimes, when we talk about the randomized things, sometimes it will answer correctly, sometimes it is not. But, yeah, let's go to the randomized one when we come to it. At this point, for every input, we should answer correctly. Is that okay? Okay. Let's take one more example to make sure that we understand this adversary argument. This is going to be graph connectivity problem. Okay. What is the graph connectivity problem? Your input will be describing a graph, and what will be your output? What will be your output?
Connected or not connected?
Whether the graph is connected. It is very clear that output is Boolean. How will you make your input Boolean?
So the graph is a undirected graph.
Yes, undirected. Thank you.
Okay, we can use an adjacency matrix.
Yes, or other way to say it is, the easier way is you just fix an ordering on all n choose 2 edges. Correct. And then my input is a string of zeros and ones of length n by n choose 2.
Yeah.
Right. So 0 means edge is not present, 1 means edge is present. Correct. So it is clear that every x of this kind describes a graph on n vertices. We assume some ordering of edges that should not be confused. Think of adjacency matrix and you go row wise or column wise. You can decide what your ordering is, but once you fix an ordering, then every x here is giving me a graph on n. Fine with that? And then graph connectivity is basically a Boolean function. Let's call this problem GC. And what are we going to talk about now? What are we going to talk about now?
D of GC.
Its complexity.
Yes, D of GC. And clearly it will be less than n choose. This is something which we don't need to worry about. If I know all the edges, then I know whether the graph is connected. Right? Because once we know the entire input, then I will do some computation. I don't care how time intensive it is, but I can do it. Right? So then this is less than n. Actually, this is not the question. It's something which we know. The question is, can you prove this? And again, to our help should be the adversary. So take some time, think about it. The problem is quite clear. Prove that the decision tree complexity of this graph connectivity problem is greater than equal to n or equal to, sorry, n choose 2 using adversary. How will you do this? I'm telling you that you can do it. Let us listen to your ideas.
So take the nth vertex or the last vertex. So let's say in the ordering of n choose 2, the last edge represented the edge between the nth vertex and some other vertex, let's say n minus 1th vertex.
Okay.
Then if the nth vertex has only one edge which is incident to it, and that edge is xn minus 1 to xn, then we have to go to the till the last edge. We have to check till the last edge.
But what about the decision tree which asks xn to xn minus 1 at the first instance?
Yeah, then formulate some other kind of graph where this just the value of n changes. It can be 1 also, the edge between x1 and x2. It's the only incident edge to x1. So we need to query x1, x2 sometime. So in this way, any edge needs to be queried for a particular input. So let's say for input one, we need to query x1, x2. For some other input j, we need to query xn, xn minus 1. So for a graph, for a tree to be correct on all inputs, all the edges are important.
Okay, let's talk about this. Okay, for y2, some other edge is required, right?
Yes.
Let's say 1, 2, 3, 4, right? So what you are saying is that your decision tree has all these edges, nothing more than that. Correct?
Yes.
So now a decision tree which has n choose 2 edges,
No.
its depth could be?
No. N choose 2 edges means n choose 2 queries in decision tree.
Yes. So how many nodes are there in a decision tree of depth n?
Okay. It can be the least. It can be log n. Yeah.
Yes. So your argument will show log n choose 2.
Yes.
Right? Which is good. It is non-trivial bound. It is more than a constant bound. But we will see that this is still very weak. We can actually get a n choose 2 bound. And again, the important point is that if you are going to say input by input, this is going to be difficult. You should think of it as an adversary argument. Think of someone giving you some edge, and how would you reply to it? You don't want to construct an input in the beginning.
Okay.
Right? You want to construct the input slowly, depending on what queries are asked by the algorithm. You are the adversary.
So if the final graph that we are going to generate is something like this, that we would have n minus vertices and there would be a tree. There would be just 3 edges connecting those n minus vertices, and there would be one vertex that we would keep free at the end so that we can tweak it, connect to any other vertex, and then change.
Right. See, this is what we have in mind, that we should have a spanning tree in the end. And then, one vertex, as you said, suppose there is one edge which will remain. That is the idea. But again, this is not an argument because you are constructing a particular input, right? And then there could be a decision tree which would ask this red edge at the first instance. But your idea is correct. You want to keep answering so that finally I have a figure like this, where there is a spanning tree, there is one edge remaining, and depending on whether I assign that edge 0 or 1, my graph will become corrected or become right. But how should I answer so that I always in the end up with this situation? Whatever sequence of edge queries someone asks, how can I reply so that my final thing looks like this?
So for fix a particular vertex, let's say x1. Okay. So any query which is related to x1 vertex, we will return 0.
Okay, sure.
So
take an algorithm which asks all the queries of x1 in the beginning.
It can ask all the queries in the first n minus 1 queries.
Yes. let's so you see that it's not as straightforward, right? For all it was very, very straightforward, correct? Now things have become interesting. So you want to see the adversary argument?
Yes.
Yes. Has it has it excited your curiosity? Okay. Let's try to see how to come up with the adversary argument of n, right? In this case, as we said, what we want to do is to answer so that the graph is barely connected. I have not described what do I mean by barely connected, but I will do it just in an instance. But this is the intuition that somehow it is barely connected, and in the end, I will probably just change the edge by 0 or 1, and then graph will remain connected or distant. This is the thing this is the same intuition which Udit did. How to do it? Let me do some color coding. I have blue edges in my graph at any point. These are the edges which have not been queried. Okay, assume that all of them were present, because I could have made them all of them to be present, but these are I'm calling blue edges. Then I have red edges, which are the edges which were queried and were answered one. Or basically, these are the ones which I have selected at any point of time. Okay, so this is an intermediate stage in my adversary argument. At an intermediate stage, some of the edges I would have answered as 1. Those are red edges. Some of the edges I would not have picked. I would have answered them 0. Those I am ignoring. Correct? So let me just say this also. Ignore which were queried and answered 0. Those are ignored, and then we have blue and red, right? So can you tell me few things which I should keep in mind while answering? How should I answer so that my graph remains connected with what edges?
If query is between two red edges, we can, I mean, it does not matter what do we answer.
You cannot have a query between. See again, we are querying edges, not vertices.
Okay, sorry, edges.
Right? So I cannot obviously query a red edge that has already been queried. We will always be querying only blue edges, but then first thing is, what should I keep constant? What should I be aiming for? I should answer so that my graph remains
Barely
should
connected.
keep
barely connected, right? But what will it mean in terms of blue and red edges?
I mean, there is
blue number of
bridge.
blue edges is more greater than equal to 1.
No. That is, yes. That is just that is what you're saying is what will happen in the end, right? But if the graph has to be seen, again, we have to answer so that finally we can make it connected or disconnected. That means at any point of time, using red and blue edges, it should be
Spanning tree.
it should be connected, not just spanning tree, right? Look at the first, when you have not picked anything. Blue is everything, so it cannot be a spanning tree.
Yes.
Yeah, but what I want is that if even using red and blue, my graph is not connected, then there is no hope of making the graph connected, right?
Yes.
Right? Because blues are the one which are left to be queried. If using all blue edges, I can't keep the graph connected, then there is no hope. So whatever I do, however I answer, I should make sure that the graph is connected means if I look at all the blue and red edges, whatever I got is a connected. Okay. So now how am I answering? This, and since I said barely connected, that means this is my adversary strategy. Since I said barely connected, answer 0, except if 0 makes this invariant go wrong. What invariant am I talking about? Do you see what I'm trying to do? Do you see the adversary strategy? Mostly I will be answering 0. I will answer 1 if and only if I remove that edge, then my graph of blue and red edges becomes disconnected. This is the way I will start answering my questions. Obviously, initial few will definitely be zeros. And then I will say, oh, if I even, so let's say one example would be, I have x1 and n minus 1 edges, and some algorithm tries to pick all the edges with x1 in the beginning. Then x1, x2, I will say 0, x1, x3, I will say 0, x1, x4, I will say 0. But as soon as it is x1, xn, I know that if I answer 0, then my graph will become disconnected. So I will answer 1. Then again the algorithm will keep asking me something. I will start, I will keep. So this is the strategy. I will keep the graph connected, barely connected. That means I will mostly answer 0. I will only answer 1 if removing that edge makes the graph disconnected. When I say makes the graph disconnected, I am talking about the graph which is made up of blue and red. Again, I haven't proved that this strategy will work, but that we will do in a minute. But is the strategy clear?
So what do you mean by an adversary?
Oh, this is just a way of giving argument. In this lower bounding argument, adversary is the person who will create an input where the algorithm cannot answer correctly.
So over here, I mean, the adversary is trying to create an input.
Right. So your algorithm is asking queries, and your adversary is giving answers such that the answer is not revealed till the end.
Okay.
Till the end means number of whatever lower bound you want to show. So seems like a good strategy, seems like a natural strategy to use. Okay. Let's prove that why will this give rise to the algorithm asking all the queries. Okay. The things which you have to notice are, can red edges make a cycle? What do you think? the way I am answering, can red edges make a cycle?
No, because choosing had we answered 0 instead of 1 using any of those any of the edges in the cycle would still make the graph connected.
Correct, because yeah, whatever the last edge you added, it should not have been added, right? This is easy to prove using induction. Pick the last edge which you have put in the cycle. Why did you pick that edge? According to this strategy, which we just mentioned, I will never put the last edge of a cycle. So can red edges make a cycle? No. That means at every instance, I will have something which I call a forest. Right?
Forest of red edges only.
Forest of red edges. Yes. Thank you. Yeah, because with blue edges, it becomes connected, right?
Yes.
So forest of red edges. Thank you. First red
So in
edges.
the proof that the red edges cannot make a cycle, what are we inducting on? The number of red edges?
It's okay. You don't even have to say induction. What I meant was that the last edge which you added, right?
Yeah.
So you say that assume there is no cycle till now. Now you add another edge. Can that edge create a cycle? So it's kind of assuming that before that there is no cycle. Now in the next
Okay,
iteration
okay,
also there will be no cycle. So I
Okay.
call it induction, but yeah, it's kind of straightforward. The last thing which you would want to prove is that you do not get a spanning tree till the end. The spanning tree is obtained at the last edge. When there are no blue edges remaining, then only you will get a spanning. Okay, and this argument you can read in the notes. I would say that you try it first as an exercise. If you can't, then look at the notes. It's very similar to saying that red edges cannot make a cycle. You have to remember that if any edge, if you take a spanning tree, any other edge creates a cycle in that span. You are familiar with that? You fix a spanning tree. If you pick any other edge from the graph, that graph is going to create a cycle in that span. This is a very, very easy fact to prove. And using that argument, you can argue that, you know, if you already got a spanning tree, there is a blue edge remaining. That blue edge would have made a cycle, and that you can. But anyway, I will not worry about it now. You can try it. I would say it's a very nice, simple exercise, combinatorial exercise. You try to do it. If not, the solution is given. But what we were able to show was by adversary argument again that deterministic query complexity of graph connectivity is complete. It is endless. So you saw two adversary arguments, one for OR, one for graph connectivity. In both of those, you got the full bound. In case of OR, there were n variables, you got n. For graph connectivity, you got n. Do you think that the deterministic pre-complexity of every function is n?
No.
No, for example, the complexity for addressing function is logarithm in a size.
Right. So you can clearly see that if you look at the addressing function, what will be the decision tree complexity of it? It will actually be log n plus 1. Remember, first log n bits give the address. So I will query the address, I will get a target, then I will query the target. If you have forgotten what the addressing function is, look at it, and this is very well. You can also show that this is type using addressing. But we are not going to check this.
So for a constant function, the The complexity
Yeah,
will
yeah,
be
but
zero.
you can always say yes, that is correct. But you can always say that the function is non-trivial. Right? Constant
yes.
functions you can do. But you are right. The decision tree complexity of a constant function is
When we are saying log n, are we rounding it up or rounding it down?
okay. Let's say that the addressing function is of the addressing t will be t plus 1, but in this case the input size will be t plus 2 to the
Okay.
power,
Yeah, yeah, yeah.
right? So the input size is much bigger, but the complexity is much.
Okay.
So in this proof that is given for graph connectivity, we are trying to construct a particular input. I mean, the adversary is trying to construct a particular input such that that depth is achieved. I mean, if I'm correct. Is that what is? I mean, what we are trying to do?
Yes. The adversary. See, the argument goes like this. Let me formalize this. The the adversary says this. You means adversary is saying to the algorithm, you pick any D queries. I can answer them in such a way that the value of function is not fixed. The value of the function depends on the remaining variables which you have not put. Okay. And then this, if there is an adversary argument like this, then D of F is more than. This is in some sense the how should I say it? This is the content of the adversary. Did I answer your question?
Yes.
Right. So actually, let's say LDF is the max D such that there is an adversary argument of depth D for F. Okay. What do I know about D of F and LD of F?
D of f is greater than or equal to LD of f.
Very good. Because if I can construct adversary argument for any D, it is a lower bound on the decision. It is smaller than DF. And even if I take the maximum of all the lower bounds, it will still remain a lower. Right? It turns out that this is actually equal with, like just plus 1. That means with adversary argument, you can give the best lower bound.
How do you even prove something like that? Like adversary argument is a kind of a proof technique, right?
Yeah.
So we are using that itself in a proof.
Yes. So let me tell you this. So suppose D is the max number for which adversary argument exists, correct?
Yeah.
So again, I have a function in mind, right? I have an F in mind. Right? For this particular F, suppose D is the max number for which adversary argument exists.
Yeah.
That means for D plus 1, there exists a string of or a sequence of D plus 1 queries, I should say adaptive queries, which cannot be answered in an ambiguous way?
Yeah.
Now these D plus 1 adaptive queries, they will give me the decision tree for it. You should think about it. This is an interesting question. It is, you have to just think of what is the definition of decision tree and what do I mean by sequence of D plus 1 adaptive queries. But if you cannot make an adversary argument for D plus 1, that means there is a sequence of queries. Those sequence of queries are exactly that is the decision tree.
Oh, yeah, makes sense.
And that will give you D of F. Okay, this was one lower bound. Let me give you another lower bound. Lower bound 2. Any guesses? What is this lower bound going to be? This is something which you have seen before.
Something related to the degree of F.
Yes, it is going to actually be exactly B. What you can show is that D of F is more than degree of F. The point, so this kind of argument, you will see many such proofs in all of these. What is the idea? You pick a decision tree for F and construct a
Polynomial for F.
polynomial. Exactly. Such that, how should you construct a polynomial for F? Such that the depth.
So we can do it based on indicator polynomials and
Very
leaf
good.
nodes.
Yes, but before we would do that, I just want to emphasize that while you do this construction, you have to remember that the depth of the decision tree should transfer to the degree of the polynomial. Correct? And then the transfer is very simple. I think few of you have already guessed it. It is given as an exercise. But what you do is, every path will give rise to an indicator function, and the polynomial representation is just sum of all the indicator functions of the leaf. This is that. And how do you create the indicator function for the leaf? You guys can figure it out. It's just a partial version of how we created indicator function for a truth table. It's very similar to that. Okay, so if there is any question, ask in the forums. I will answer. But you should be. But it's a good exercise to do. Given a decision tree for a function f, I want to create the polynomial for it, and this is the way to do it. I will look at every path. Every path corresponds to every leaf. There is an indicator for every leaf. I just add up all those. Actually, I should say the leaves which give the answer 1. So sum up over all indicators of leaves which are giving answer 1. That will be the polynomial representation. Verifying that this works is an exercise. Is the idea clear? Questions about this? If we went too quickly over it.
Is this bound tight or anything?
No, it is not. That's going to be our next question. But df is more than degree of f. How will you prove it? The idea is clear. Correct? I'm not saying all the details are clear. That obviously is part of exercise. But is the idea clear? The terms which I have defined it on this slide, are they okay?
Yes, sir.
Yes. Okay. Then let's take the other side. Can we say that degree of f is more than d of f? You can show that this is not true. A simple example would be majority of, you have to pick odd or even or something. This could become n minus 1, but this, sorry, this will be n, but the degree can become n. Okay, so you can arrange in such a way, you can pick n nicely and do some stuff, and you will see that the degree becomes n minus 1, but d of f is more than. In all of these situations, so let me say some of the things, some of the questions which we generally ask whenever we have multiple complexity measures, right? The first is obviously relation between the two complexity measures. Let's say now in this case, degree f and df. We know one, degree of, sorry, I should say, degree of f is less than d of f. This we know. We want to ask other way. The best we know the other way is that degree cube of f is more than d of f. This proof will be done later in the course.
So, sir, what about the equality?
The equality is not there, I told you, right? This degree of f is equal to d of f cannot hold true for all f. This is an incorrect statement. For some functions, d of f could be degree of f. What we know is that df is definitely less than degree cube of. So for all functions, we know that degree of f, d of f, they will obviously satisfy this. And once these relations are established, remember second will be proved later. First we have just proved. The next question is there a function where this thing is tight? So can you give me a function where this, the thing I am pointing to is tight?
Or function, and function.
Or function, and function, actually most of the symmetric functions. You can show that this is true. So this is or. Now you can similarly ask, are there functions for which this is true? That means, are there functions where df is equal to degree cube? We don't know yet. The best we know is that there exists f such that d of f is more than degree square. Okay. Again, this function is not easy to construct, but recently, like I think 5-6 years back, using some pointer kind of thing, this function was constructed. But this is the best separation we know between df and degree square. That means the question still remains open. In the future, someone might be able to prove that d of f is less than degree square f, or we might be able to prove that there exists a function such that d of f is omega of degree cube, or this exponent might be 2.5 or 2.1. We don't know. But this is true. So you understand, these are the kind of questions we ask about complexity. This is how we want to relate complexity. We want to give both upper and lower bounds. And once we give upper and lower bound, we want to show that there exist functions for which this thing is set. And if we don't show it, then probably the lower bound or the upper bound can be improved. This is the general philosophy of relating these complexity functions. Questions on this? Did I go too quickly on this? Did the question seem natural? Think of it this way. Given deterministic pre-complexity, what can we say about the degree of the function? Are they very, very close to each other? Are they far apart? And if they are far apart, then you want to give an example where they are far. That is the kind of thing which we did, right? We constructed a function which for which df and degree square f were further. So you should be very careful about quantification. When I wrote this equation, this is true for all functions. The bottom thing written in red is, this is an example. This is a particular function for which df is more than degree square. This does not mean for every function d of f is more than degree square. This means there is a particular function for which this happens. Questions about this? I just need 5 more minutes. Should we move ahead? Or there are questions? Okay. Another natural question which people ask is about the composition of function. Right? D of f composed with G. What would be your guess? If you can solve G, if you can solve F, how will you solve F composed with G? What is the
D of f times d of g.
Yes. What will be your strategy? You will solve the individual G's first. You will calculate this, then this, then this. When all are there, then you go up and solve F. This is the dumb, but seems the most natural way to solve F composed. If you do that in the deterministic model, your guess would be that this is equal to df times t. Notice that when you construct an algorithm for f composed with g, you are only showing
An upper bound.
Upper bound, yes. So this we know. This is also given as an assignment in the exercise, as an exercise in the assignment, just to make this argument formal. How to make a decision tree of f composed with g, given given a decision tree for f and given a decision tree for g. This, in most of the computational measures, this is always the easy part. Most of the algorithms compose naturally, right? You can think of, here we are making a decision tree, but even if there was an algorithm, the idea is clear. You first solve G, all the copies of G. Once you have done that, then you solve the copy of, and you are right. So this should not be surprising. Right? Now, you might ask, is this also true? And these are harder questions. These are the questions when you want to compose the lower bound. Let me show you one way, one lower bound which can compose. Can I say this?
Yes, obviously.
Obviously, right? Because f composed G also is a Boolean function, and we know for all Boolean functions, decision tree is more than degree. What do you think will be the degree of f composed with G?
Multiplication of the 2 degrees.
Why?
Because basically it's something like if you take the maximum in G, the maximum, I mean, parity that is contributed,
Hmm.
then that will be what I mean. One of them will also be the maximum that contributes in.
So what you are doing is you are taking a polynomial of f, you are taking a polynomial of G, and you are saying that will give me a polynomial of f composed with G.
Yes.
Correct. And then you are saying, but why is that the best polynomial? Why can't you create some other polynomial whose degree is lower?
Because it's unique.
Very nice. So here you get the equality actually very, very easily. This doesn't happen in most of the cases. But degree is very, very nice. You get the lower bound because as soon as you construct a polynomial for f composed with G, it is the best polynomial for f composed with G also. Follows from uniqueness of polynomial. Right? Once more, what is the argument for this inequality? First, you use polynomial representation of f and G to construct polynomial for f composed, and you will see that the degree multiplies. This is the easy part. Then the next point is that this constructed polynomial is the best polynomial. Why is this best for f composed with G? Because there is only one polynomial. We know that there's only one polynomial which can represent f composed. So once we have constructed the polynomial, that has to be best for f composed. And this is easy. So for today, I would just like to summarize that the take-home message is that what do we do generally with complexity measures? We define the complexity measures. We start seeing its relations with other complexity measures. Today, we saw a relationship measure between df and degree f. D is the deterministic pre-complexity. Degree f is the polynomial degree. And we gave relations. We realized that df is more than degree, but the upper bound only comes with degree 2. That's the best we know. It could potentially be improved to degree square, or there might be functions for which df is as big as degree 2. We don't know yet. It's an open problem. You solve it, you can write a paper. Okay. But other kind of questions which you can ask is what happens when you compose a measure of complexity? And then again, most of the time, upper bounds are easy, lower bounds are tough. This finishes the lecture for today.